We're going to look at the quotient rule with this lesson. If you are a random person coming by on the internet who just happened to stumble across this video and you want to print the guided notes sheet that I give my students, you can go to this bit.ly link right here. That is case sensitive. So let's go on and look at the quotient rule. And I am assuming you already know the product rule. That is typically taught before the quotient rule. So if you don't know the product rule, you may want to watch a lesson on that first. So the quotient rule, as you may have guessed, is used for functions that are in the form of f of x divided by g of x. Remember, a quotient is what you call the answer to a division problem. And the times you want to use the quotient rule are when your functions on top and bottom, when your numerator and denominator both have an x in them. If your numerator or your denominator is just a constant, we will avoid the quotient rule. And the quotient rule is, in my opinion, the ugliest of all the derivative techniques. I don't know if it's the hardest, but it's the ugliest. And something to always keep in mind is before you just dive into derivatives, always consider algebraic techniques that may allow you to simplify your function that may look like a quotient or it may look like a product, but you could do some algebra that would turn it into a power rule. So always pause just for a few seconds and think about derivatives. Think about algebra before you just jump into a more complicated derivative technique, those being the product rule, the quotient rule, and eventually you're going to learn about something called the chain rule. So what I have right here, I have 5 different functions, and we're simply going to look at these and determine if we should or should not use the quotient rule. Every one of these are written as a quotient, so you could use the quotient rule on every one of these, but let's decide if it's needed. And so number one, not really numbered, but e to the x divided by x squared minus 7x. Would you use the quotient rule on that one? And my answer is yes, I would, because I don't see any way that I can easily avoid the quotient rule for that problem. Now, just this one time, I'm going to show you something you could do, and I'm going to erase this. You always have the option, every single quotient you see for the rest of your life, I believe, you always have the option of grabbing that entire denominator and multiplying by the numerator, but raising it to the -1 power. So by doing that, I have turned my original problem into a product rule. However, while you may prefer the product rule, right here we have something that would actually require the chain rule. We have something ugly to the -1 power. So I did turn that into a product, but it's now a product with a chain involved, and we have 2 derivative techniques. I think it would be easier just to do the quotient rule with the original problem. So I would absolutely use the quotient rule on the first one. Let's look at the second one, 4x cubed minus 16x over 8x. And would you use the quotient rule on that? While you could, I would not, because here I have one term in the denominator, and I call this an STD, a single term denominator. And if you have a single thing in the denominator and you are adding or subtracting in the numerator, then you could rewrite this function as 4x cubed, the first term divided by the denominator, 8x, and then it's minus 16x over 8x. And if you simplified that, if you clean that up, 4 over 8 is 1/2, x cubed over x is x squared, and 16x over 8x is 2. And so by doing a little bit of algebra, I was able to rewrite that function as just 1/2 x squared minus 2, and that is a very, very, very convenient power rule. As a matter of fact, so convenient, I'm going to go ahead and knock that out. The derivative of that function would just be x. And so that's a whole lot easier than the quotient rule, which you're about to see. All right, the next one, 3x squared plus root x over x plus 1. That is a quotient. I do see variables on top and bottom, and I don't see any way that can be rewritten to conveniently avoid the quotient rule, so I'm just going to go on with the quotient rule on that one. The next one, 7 divided by that stuff. I would not do the quotient rule for this one, because my numerator is not a variable expression, it is a constant. And so what we will do for problems like this one, if your numerator is just a constant, we will rewrite the problem using the same trick I showed you initially in the first one. However, this would turn into 7 times the denominator, 3x to the 4th plus 2x to the -1 power. And here we can finish this with the chain rule, which you may not know yet. However, it is my opinion that the chain rule is easier and it's definitely quicker than the quotient rule. So in this case, I would avoid the product rule, excuse me, the quotient rule, and I would do the chain rule for that one. And then the last one, 1 plus sine x over cosine x. There are variables on top and bottom. However, again, I have a single term in the denominator. And so we can use our STDs. Got to get rid of those STDs, right? And I can put each of those terms in the numerator over the cosine x, which would be 1 over cosine x plus sine x over cosine x. And if you look at those individually, those can be rewritten as, well, 1 over cosine is cosecant x. No, it's not. It's secant x. And sine x over cosine x is tangent x. And by the end of this lesson, if you don't already know them, we will have the derivatives of secant x and tangent x memorized. So we're going to add the rest of our trig functions to the memorization bank. And once I rewrite that function by using STDs, I have something I can very quickly just spit out the derivative and avoid the quotient rule altogether. So we've talked about the quotient rule. We've looked at functions when we would use the quotient rule and when we would not, but I have not yet shown you what the quotient rule is. So here is the quotient rule. If you have a function that is written as f of x divided by g of x and you cannot simplify it to avoid the quotient rule, then this is the quotient rule, and it is not very pretty. It is your denominator times the derivative of the numerator, so g f prime. Notice we are subtracting here. I'm going to talk about why that's important in a second. So bottom derivative top minus the top function times the derivative of the bottom function. And then all of that divided by the bottom function squared. And if you look at that numerator, a point of emphasis, it looks like the product rule, but it's not as forgiving as the product rule because this is subtraction. Because that's subtraction, you absolutely must begin with your bottom times the derivative of the top. Unlike the product rule, you cannot reverse that numerator because of the subtraction. If you do the numerator backwards, you'll have the right looking derivative, but it will be the exact opposite. It'll be the negative of whatever the derivative should be. So make sure that you do bottom derivative top minus top derivative bottom over the bottom squared. And then a less formal way of saying this, and I think just about every calculus teacher in the world uses this expression because it's just fun to say. If your numerator is the high function and the denominator is the low function, then your derivative is low d high minus high d low over low low. Low d high minus high d low over low low. And d high just means the derivative of the high function. D low means the derivative of the low function. So it's a more fun, catchy way of saying the quotient rule to help you remember that that numerator must begin with low d high. Absolutely must begin with low d high, high d low over low low. And let's put this into practice. So I have a few examples. I think I have 4 total. And the last one takes us to the memorized trig derivatives. So here we have a function. It is a quadratic over a cubic function. I don't see how any amount of algebra is going to make this convenient to avoid the quotient rule. So I'm going to jump into the quotient rule and my derivative, f prime of x. Remember to label your equations. This is f prime. So write f prime equals, please, is low. I literally copied the low function. Low x cubed plus 2x. D high, so I'm looking at the numerator. How do you differentiate that numerator? Well, it's just a power rule. Derivative of x squared is 2x. Derivative of 3 is 0. Low, d high, minus high, x squared plus 3. So I copy my high function, my numerator, times the derivative of the denominator. And the derivative of the denominator is 3x squared plus 2. And then all of that is over the denominator squared, x cubed plus 2x all squared. And there's your derivative, low d high minus high d low over low low. And I'm going to clean this up in just a second. I'm going to pause the video and clean it up and talk about how you would simplify this if you need to. However, before I clean this up, I very intentionally made a very common mistake that many students make as they are doing the quotient rule, and it is right here in the second term. When I did high d low, 3x squared plus 2 is the derivative of that denominator. However, by not putting it in parentheses, the only part of this that is being multiplied by the numerator, by the x squared plus 3, is the 3x squared. That plus 2 is outside the multiplication there. So make sure when you are doing the quotient rule I strongly recommend that you always put your low and the D high and the high and the D low, always put them in parentheses, even if it's not needed. That way you're safe. You're covering all your bases. Notice I put parentheses around the 2x. I didn't really need them because there's no addition there to worry about, but it's good practice. Just go ahead and put all of those pieces in parentheses so we don't have to worry about it. And so now as far as the simplifying, I'm going to clean up this one function and that's it, just to kind of show you what the simplifying would look like. In the quotient rule, if you need to clean up your first derivative of a quotient rule, first, do not expand the denominator. It is very seldom, it is very rare that expanding the denominator helps. So I'm just going to leave that there and I will not expand the denominator unless there's something in the problem that makes me think I should really expand this. And that almost never happens. The numerator, however, we will fully expand the numerator, combine like terms, and sometimes you can continue to factor what you have after you combine like terms. And I'm going to pause the video and clean that up. If you want to pause as well to see if you can simplify this and get the same thing I do, then you can do that. And I'll be back in about a second. There was 1 second. And here is my simplified derivative. So I distributed my 2x through that first piece. Here I expanded the x cubed, x squared plus 3 and 3x squared plus 2 to get this polynomial up here, distribute the negative, combine like terms. And a lot of times this is where you can stop. You can't really do much else with that. But I noticed, coincidentally, that if you factor out a -1, you can factor x to the fourth. Here's a typo. X to the fourth plus 7x squared plus 6. Which factors to x squared plus 6x squared plus 1. There's really no advantage in doing that because nothing were cleaned up really beyond that. But that would be the factored and simplified version of the first derivative f prime. So let's look at some others. Let's look at this one. 2 to the x over x cubed plus 5. Again, I'm considering options that would allow me to avoid the quotient rule, and I don't see any convenient ones, especially since that's an exponential over a polynomial. I'm going to go on into the derivative. So dy dx, or you can call it y prime if you so desire. Low, copy the low function, x cubed plus 5. D high, now here's one that people often forget. The derivative of an exponential function, if your base is a constant and the exponent is x, is a to the x times the natural log of a. And people forget about that natural log of a part. So the derivative of 2 to the x is going to be 2 to the x, natural log of 2, minus, so that's low d high minus high, 2 to the x. D low would just be the derivative of x cubed plus 5, that's 3x squared, all over low, x cubed plus 5, all squared. And this time I'm not going to do anything to this. I'm just going to leave it like this. There's no advantage in cleaning it up. And again, this lesson is really just to get you familiar with performing the quotient rule. The simplifying and using the resulting derivative comes in things later on in the year. So there's my derivative here. I believe that all looks good. Low d high minus high d low over low low. Looks good, looks good. Onward, number 3. So what I'm going to do on this one, I'm actually going to pause the video and I'm going to work the derivative. I'm going to work the derivative and just show you my answer here in a second. And just kind of see if this is what you did as you encountered problem number 3. So if you want to pause yours for a second and try it, you can. I'll be back in a second. And I'm back. And so here is what I get when I do my initial pass at the derivative. I'm not going to clean this up any, but I did the quotient rule. Low, x squared. D high is 4x cubed plus 2 minus my numerator, my high function. D low is 2x over low. And this is a correct derivative. There's nothing wrong with this. However, it's kind of ugly. It's going to be very difficult to use if we have to use the derivative to answer another question after finding the derivative. And this is a problem where I personally would not have done the quotient rule because you should always pause and think for just a hot second. Can algebra help you avoid the quotient rule? And in this case, you can. This is, again, an STD. We have one term in the denominator. So you could have rewritten this function as x to the fourth over x squared plus 2x over x squared plus 1 over x squared. Now we have 3 different terms that will all reduce to power rule derivatives, which in my opinion is better than the quotient rule. Another way you could clean this up, if you don't like the STD, the separating the numerator over your denominator approach, another way you can do this one is you could bring that denominator up, it's x squared, you could bring that denominator up as x to the negative 2, and then distribute that x to the negative 2 through that polynomial that is the numerator. And if you distribute that, I have an expression for h. Just remember, when you distribute, you add exponents, same base, you add exponents. Negative 2 plus 4 that'll be x squared. Negative 2 plus 1, that would be 2x to the negative 1. And x negative 2 times 1 would be x to the negative 2. And now we have a very nice, clean power rule. My derivative would be 2x. Negative 1 times 2 is negative 2. X to the negative 1 minus 1 is negative 2. And then bring on the negative 2. X, negative 2 minus 1 is negative 3. So that is a much cleaner, nicer derivative than this quotient rule right here. Then I have one more example I wanted to look at, and it is the function tangent x. And you're wondering, why in the world is f of x equals tangent x in a lesson about the quotient rule? And that is because you can, if you don't know the derivative of tangent x, but you do know the derivatives of sine x and cosine x, which my students should, the derivative of sine x, and I'm going to rewrite tangent as sine over cosine, and now I can get the derivative of tangent by using the quotient rule with sine x over cosine x. So I'm going to, again, for the sake of time, I'm going to pause the video. I'm going to work through the quotient rule of sine x over cosine x. Then we'll talk about what that cleans up to in a minute. Okay, I lied. It was a minute in real time, but I forgot I was pausing the video, so it's a few seconds to you. But there is the initial pass of the derivative, low d high, derivative of sine is cosine, minus high d low, derivative of cosine is negative sine over low low. And while that is an acceptable derivative, boy, this cleans up quite sexily. So let's see what happens here. And my derivative is cosine times cosine, that's cosine squared x. Negative sine times negative sine is positive sine squared x, and I'm going to rewrite cosine x squared as the cosine squared of x. And you should hopefully know that sine squared plus cosine squared, or cosine squared x plus sine squared x, is 1. 1 over cosine squared x is what this cleans up to. But wait, there's more. Because you should also know that cosine and secant are reciprocals. So if you have 1 over cosine squared, and 1 over cosine is secant, then 1 over cosine squared is secant squared x, and that is the derivative of tangent x. So for the rest of your life, if you need the derivative of tangent x, you can just say secant squared x. You're expected to know that. Please don't go through the quotient rule, although you could if you forgot the derivative. And with that, I'm going to go ahead and give you all of the trig derivatives. You should already know, I think, well, my students already know, that the derivative of sine x and cosine x are cosine and negative sine x. And I'm going to go ahead and give you the other 4, and every one of these can be written in terms of sine and cosine and quotient ruled. Cotangent is cosine over sine, secant is 1 over cosine, cosecant is 1 over sine. So you have that option, but it is a heck of a lot easier to just memorize these. We just did tangent. Derivative of tangent is secant squared x. Derivative of cotangent is negative cosecant squared x. Derivative of secant x is secant x tangent x, and yes, there is a secant and a tangent, and they both get an x. And the derivative of cosecant is negative cosecant x cotan x. And there are your 6 derivatives. You can look at whatever patterns you need to help remember them. Most students just memorize them brute force. The one thing I want to point out is notice that all of your co-trigs, cosine, cotan, and cosecant all have negative derivatives. So just something that might help you remember where the negatives belong, but it's up to you to remember the rest of it, and really it's more efficient just to memorize those derivatives, because the option other than memorization would be to quotient rule, and man, that is just not effective. So there's our quotient rule lesson, and I hope that made sense to you.